When working with problems that involve a variable amplitude, one particular application comes to mind, which is that of a spring that's vibrating back and forth, but with friction to slow down those vibrations. These situations are known as damped harmonic oscillation, and we're going to take a look at the shape of those things as we work through this problem. A spring with natural length 20 feet is pulled back 6 feet and released. It oscillates once every 2 seconds. Its amplitude decreases by 20% each second. Model the position of the spring t seconds after being released. Now, these problems are set up in a number of different ways. Sometimes you have something hanging from the ceiling, but since this says pulled back, the implication from that, for me at least, says that it's held horizontally. So you've got a spring and it's attached to a thing that you can grab onto. Right? And so the natural length of the spring, well, natural length of the spring is the spring when you're not adding extra force to it. And so that natural length is going to be 20 feet. And then what's going to happen? It's going to be pulled back by 6 feet. So pulled back, think back away from the wall. And so if it's pulled back by 20 feet, or by 6 feet, then the 20 feet becomes 26 feet. And then when you let it go, what's going to happen? Well, since you're pulling back on the spring, when you let it go, the spring is wanting to pull back, so the box, or whatever it is it's attached to, will swing back this way. But because of its momentum, it will typically go past the 20 feet and get short, and then get long again and short, and you'll get this vibrating pattern like this. And so we would need to try to create a model for this. So let's take a look. Now, just as we did before, we're going to try to pretend everything is going to pretend that everything has fixed values first, and then consider what's happening with the variable aspect of it. So 20 feet is the natural length. We pull it back 6 feet, so we pull it back to 26 feet. And if we let it go, it'll oscillate back and forth. And the low value is going to be whatever it is, in this case 14. But the thing we want to think about is the period, because that's what this picture is helping us to get. So it oscillates once every 2 seconds. So after 2 seconds, it's repeating itself. This part is giving us information about the b value. B is 2 pi over the period, which in this case is 2 pi over 2, which is just pi. The other thing we get from this graph is that we have a cosine function, because we're starting at the top, it's going down back up, so it's a positive cosine function. So the y value is going to be equal to a positive something, because that's the amplitude, which is the variable part, cosine of pi t, and then in this case the midline is constant, so that part is just going to be plus 20. And really we need to figure out what's happening here with the amplitude. And that part is embedded right here. The amplitude decreases by 20% each section. Now, just like the example with the population growing at a certain percentage rate, we had an exponential function. The same thing's going to happen here. Since it's going to decrease by 20% each section, we're going to subtract 20% each second. So it's going to be 0.8 to the 2th power. Whoops. That's the amount it's going to change by, 0.8 to the 2th power. But then we also have the initial 6 feet. Right, so this value right here, it feels like it comes out of nowhere at first. With a little bit of practice and experience, it feels much more intuitive. Basically, what it's saying is that we're starting off with 6 feet of oscillation. 1 second later, it's going to be 6 minus 20% of 6. 20% times 6. And so then when you factor out the 6 on this, you get 1 minus 20%, or 1 minus 0.2, which is 0.8 times 6. And then the next stage is going to be 20% away from this. So 6 minus 20% times 6 minus 20% of that part. And I'm running out of space here, but this is exactly the same calculation we did with the population model previously. And so you're going to factor out another 0.8, so it's going to be 0.8 to the 10th power times the 6. And so this is what leads us to this value right here for the variable amplitude. And when we go ahead and graph this, I'm going to erase this part right here. When we go ahead and graph this, here's what it'll look like. Here's our midline at 20. It starts off up here at 26, but then the vibrations get smaller and smaller and smaller. And that corresponds to friction slowing things down, and eventually it'll look like it'll settle down. So here's one example of using damped harmonic oscillation, or doing a damped harmonic oscillation model and using a variable amplitude to do it. Here's another problem of the same type. A spring with natural length 30 centimeters is pulled out 10 centimeters and released. It oscillates 4 times each second. After 2 seconds, the amplitude has decreased to 5 centimeters. Model the position of the spring. All right, so once again, we're going to think about everything as if there is no changing amplitude, and that will get us started. So it's going to start off with a natural length of 30, and we're going to pull it out 10 centimeters. So pull it out sounds like it's getting longer. So it's going to be 40. It's going to start up here, go down and up, and down and up, and so on. Now in this case it says it oscillates 4 times each second. So if it oscillates 4 times each second, when does it repeat for the first time? And this is something that students get messed up with all the time because they're not slowing down to think about the words of the word problem. They'll just say, okay, well, the period is 4. That's not what this is saying. 4 times per second, meaning that in 1 second it does this 4 times, which means that it takes a quarter of a second for it to repeat. So the period is a quarter of a second. Very confusing for students if you're trying to go too fast, but if you just slow it down and think and read the words, it's much easier. So our b value, which is 2 pi over the period, is 2 pi over 1/4, which is going to be 8 pi. Right? And again, we can also see here that's going to be a cosine function, positive cosine function, because it's starting at the top, going down and going up again. So y equals something something cosine of 8 pi t, and then our midline is also constant, so we can put that in, plus 30. So then we have to deal with this changing amplitude, the variable amplitude. So the only part of this problem that tells us there's a changing amplitude is that after 2 seconds, the amplitude has decreased to 5 centimeters. So at t equals 0, we have an amplitude of 10, and at t equals 2, the amplitude is 5. And we are trying to come up with some sort of expression that captures this behavior. Now, in general, what our formula will look like, it'll always look like some sort of constant times another constant to some power t, right? So this is usually the initial value, and this is the percent decrease. And our job is to figure out what these things are. Well, the initial value, obviously, that's going to be 10, because then when t equals 0, that's the starting point. So it's going to be 10 times something, something, something to the tth power. Whatever this value is, has to have the property that when t is equal to 2, this is going to be 1/2, because the new amplitude is going to be half of what it was before. So it has the property that x squared, when t is equal to 2, is equal to 1/2. Now this, again, this will take a little bit of practice, and in a class that was more focused on probably more like a physics class where you have to do this a lot, we'd spend a lot more time with this. For now, I just want to sort of keep our eye on the sort of big picture here. We are just going through this process to figure out what the percent decrease is per second. And so this tells us that x is equal to the square root of 1/2, and if you actually work that out, that ends up being about 0.707. And so our y value, again, I've left myself not enough room, is going to be the initial t times 0.707 raised to the tth power. Alternatively, you can leave the exact value there, 10 times square root of 1/2 to the tth power, cosine 8 pi t, plus 30. So for these problems and the problems with the variable midline, the ideas here are, again, we're not going super deep into this, we're just sort of showing you the ideas. And most of the setup here is exactly the same setup as we did before. The only thing that we're changing is either going to be the amplitude or the midline. And then that comes from reading the words and just setting up some basic equations. For this class, it's either going to be a linear changing amplitude, or excuse me, a linearly changing midline, an exponential changing midline, or an exponentially changing amplitude.